All right. And so our lesson today, guys, is going to take what we did with first derivatives and go one step further. However, and literally, Michaela's right. Second derivatives is where we're going to go. And curiously enough, the majority of the technique that we're going to use today is identical to what we did yesterday with maxes and mins and increasing and decreasing and local extrema, okay? However, we're going to use different phrases and we're going to have a different analysis of it, okay? So here's what I got. Here I have a curve. If I asked you guys about the slope of that curve, could you give me a slope of that curve? Oh, come on, don't shake our heads. No. Sure it is. It's a curve. Does it have a slope? Yeah, because it's what? Linear. Yeah. Does the slope ever change? No, right? So this has a constant. This has a constant slope. We know that, right? This always has, maybe I'll say a slope of 1/2. 1/2 all the way down, right? Here's another curve. Does that curve have a constant slope? No. In fact, what I'm going to do is I'm going to put I'm going to put 7 points on there. And I'm going to ask you guys to just shout. What's the slope here? Give me a number. -8, sure. What's the slope here? Sure. What's the slope here? Sure. What's the slope here? 0. What's the slope here? And you want to just go with 4 and 8? Wonderful. Now, guys, using these 7 numbers, we know that this portion of the graph is decreasing because the slopes are all what? Negative. And we know that this portion is increasing because the slopes are all what? Positive. And we know that that's a minimum because I went from decreasing to increasing. Now, what if I asked you not to describe this, but to describe the numbers now? What's happening to these numbers? They're actually getting bigger all the way through, aren't they? These numbers are getting bigger all the way through. Now, when I ask you how the slopes are changing, aren't I describing a second derivative? Because what is a slope? Well, these numbers that are on here are the way that the actual curve changes, right? First derivative. But when I ask you how the slopes are changing, change of slope, second derivative. Is that cool? Now, how else could it look? Well, it could look like this. And if I put 7 points and I use Michael's numbers, well, what's happening here? As I go left to right, the slopes are all what? Getting smaller. So here the slopes are getting smaller, here the slopes are getting bigger. Everybody okay with that? Okay? All right, so this is where the slopes are increasing. Here the slopes are decreasing. All right, new phrase. These three curves, guys, have what I'm going to call concavity. Now, you've probably heard that phrase used already, right? Okay. This does not have concavity. Okay? The reason that it doesn't have concavity is because the slopes are what? Constant. Okay? If the slopes are increasing from left to right, this is concave up. The reason it's concave up is because it looks like a cup. Right? Here, the slopes are decreasing. When the slopes are decreasing, we're concave down because it looks like a frown. Okay? Concave down looks like a frown. Concave up looks like a cup. Decreasing and increasing, intuitive, right? Just what you would imagine. So, all of that is sort of paraphrased down here. Cool? All right. Let's use that phrase that we just talked about with frown and with frown and cup. Would you guys agree that these two pieces down here make up that of a cup? Okay? If it's shaped like a cup, it's concave up, and the derivative is greater than, I'm sorry, and the second derivative is greater than 0. So for both of these pieces, the second derivative would be greater than 0. Now for these two pieces create concavity shaped like a frown, which means we're concave down, and when we're concave down, the second derivative is less than 0. Cool? Now I want you to go back to yesterday's lesson, or the last couple of lessons. Is this piece of the curve increasing or decreasing? Left to right, it's getting bigger, right? So this piece is increasing, so the first derivative would be greater than 0. This piece, as I move left to right, the graph is getting lower, so the graph is decreasing, so the first derivative is less than 0. What's this curve doing from left to right? Getting smaller, so the first derivative would be less than 0. In this piece, left to right, it's getting larger, so it is increasing, and the first derivative is greater than 0. So far, so good? All right, I want you to highlight a couple of things in this next box, okay? I'm going to introduce a word. It's called inflection point. An inflection value is, first of all, a value that is what? In the domain, right? Obviously, an inflection value can't be not in the domain. And it's where a graph changes from concave up to concave down, or concave down to concave up. Guys, that should sound real familiar, shouldn't it? Because where does a local max or min occur? Where a graph does what? Changes from being increasing to decreasing, or decreasing to increasing, right? Well, where does an inflection point occur? Where concavity changes from concave up to concave down, or concave down to concave up. And it has to be within the domain of the function. The same way that a max or min has to be within the domain of a function. So where I said that we were going to take one step, I'm really having the same argument, aren't I? Okay. Guys, do you see how this right here is kind of like a combination of both of these? I go from being concave up to concave, actually the other way. I go from being concave down to going to be concave up. Was there a change in concavity? So I have an inflection point where the concavity changed. Do we see that that piece is a frown, and that piece is a cup, and the spot where it switched is your inflection value. What's this? Concave up or down? Up. Concave up or down? Down. So this must be a inflection point. Now, does the derivative exist here? No. But that's okay, right? Because we'll come to that. We'll come to that. Hold on to that thought. What's this? Concave up. What's this? Concave up. Did concavity change? So is P an inflection point? No. Concavity down. Concavity up. Where did it change? Well, it changed somewhere along asymptote. But hang on a minute. The asymptote's a line. It's not a point. And furthermore, what does an asymptote imply? That the function didn't exist. And can inflection points occur where functions don't exist? No. So there is no inflection value here. Cool? Guys, I'm knocking it out of the park, right? Yeah, I told you. So that brings us to the following. And it seems like there's a lot going on here, but really not. A PIV is what I'm going to call a potential inflection value. And a potential inflection value has to first of all be in the domain. We already said that. And where do you think they occur? Where the second derivative equals 0, or where the second derivative does not exist. They are essentially critical values, aren't they? So potential inflection points are critical values, except they're of the second derivative, not the first. A graph can change its concavity at an inflection value or at a discontinuity. So inflection points can be at discontinuities. An inflection point can occur at possible inflection values, but not every possible inflection value is an inflection point. The same way, guys, not every critical value is a max or a min. Some of them don't work. So how are we going to figure out concavity? Well, we're going to do the following. Ready? From A to B. From A to B. Down. From B to C. So I'm down. I'm up. How about from C to D? I'm down. How about from D to E? How about from E to H? How about from H to K? Down. So what do you think are the potential inflection values? Now remember, potential inflection values are places on the graph where I think concavity changed, places on the graph where derivatives don't exist, places on the graph where I have discontinuities. So, by the way, endpoints aren't going to play in our reindeer games the same way that they didn't with maxes and mins, okay? So, is B a potential? Yeah. Is C a potential? Yeah. Is D a potential? Yeah. Is E a potential? Okay, I'm going to say yes for this reason. What does the derivative not do there? Exist, right? So if I work backwards, potential exists that didn't exist at other spots as well. How about H? Seem good? Now, these are what I'm going to call my potential inflection points. Now let's actually use the definition of an inflection point. An inflection point occurs when the concavity changes and the point exists on the curve. Inflection points occur at values where the concavity of a curve changes from up to down or down to up and the inflection point is in the domain of f of x. So, down, up, does B exist? Yes, so B is an inflection point. Up, down, does C exist? So C is an inflection point. Down, up, does D exist? Yes. Up, up, not a change in concavity. Up, down, does H exist? Yes. But does H exist? Does H, the point, exist? Yes, because what did I say? I said inflection points can occur at discontinuities, right? And H is a discontinuity. Cool? Now, guys, if this was just what? If this was just open, then it wouldn't be in the domain. And so it would not be an inflection point. Cool? List this graph as concave up, concave down, or constant. Well, I already did that. The arrows are there, right? We'll do it. CC up, CC down. So down from A to B, up from B to C, down from C to D, up from D to E, up from E to H, and down from H to K. All right. So we've done all of this analysis and talk about what these look like. We haven't done anything involving the actual calculus, have we? Right? So some important things we're going to do before we're going to get into the calculus. Important idea number one, not every PIV is an inflection value. concavity can happen at discontinuities, such as vertical asymptotes, right? We can have concavity changes at discontinuities, but they won't be inflection points where at the vertical asymptote. It's possible to find inflection points by finding where second derivatives equal 0 or are undefined. A chart can help us efficiently do that, just like we did last lesson. Example A. Now, we're probably going to spend at least a full day going over these examples, okay? We're probably only going to get through 3 of these right now, okay? Just because there's a lot to talk about. So what do I want to know here, guys? I want to know what are my PIVs, right? What are my potential inflection values? What are the actual inflection values? And give me the concavity of the curve. Fair enough? What is my first derivative? Cosine of x. What is my second derivative? Negative sine of x. Okay. Wonderful. Well, what do I want to know about negative sine of x? I want to know the PIVs. Where do the PIVs occur? At discontinuities, and where the second derivative either is 0 or does not exist. Well, negative sine of x is a continuous curve, isn't it? Great. Can this ever equal 0? Sure. Where does negative sine of x equal 0? At 0? At pi? And at 2 pi. Now, fortunately, they limited the domain, otherwise you would still be talking. These are my PIVs. So what am I going to do? Do a sign analysis, right? Now, guys, what is the sign analysis going to do? It's going to describe the concavity. By the way, I made a mistake. There shouldn't be any what? Shouldn't be any arrows, right? All right, so we're doing a sign analysis with my second derivative, right? Give me a value in that first interval. Pi over 2. Sounds awesome. What is sine of pi over 2? What is sine of 90? 1. Now it said negative sine of 90. Negative 1. All right, 3 pi over 2. That's in that next interval, right? Talk to me about sine of 3 pi over 2. It's negative 1. So what's negative sine of 3 pi over 2? Positive 1. So what does that mean? It means I was concave down from 0 to pi. I was concave up from pi to 2 pi. Is my PIV an inflection value? Did I have a change of concavity? And is it defined within the function? Yeah. Sweet? Sweet. All right, this next problem, we're going to get some time. Yeah. Endpoints. Endpoints cannot be inflection values, but they can be beginning and ending of intervals. Guys, if what we just did right there made sense, you understand this lesson, okay? What's going to happen now? The algebra is going to get hard. Yeah, I mean, the algebra is going to get hard. The algebra is going to get hard. So, yeah, this next one's going to take up some room, okay? Yeah, I do, actually. I got lots of extra paper. Boxes? Oh. You are. It's just plain white. Right. Paper? Wow. You want some? No, thank you. Okay. So, guys, obviously in example B, we're going to wind up having to use a chain rule. And so yeah, the calculus, the actual technique of differentiation becomes more hard. The concept does not. Okay, the concept does not. So let's see if we can do this. All right, so my first derivative is a chain rule. So let's go inside out. Inside, 2x. Outside, -6. Leave the inside alone. To the -2. All right. I can make that look a little bit nicer by simply combining those first couple terms, right? And so you look at that and you're probably pretty confident. You're like, oh, good. All right. Yeah, I could do that. I remember the chain rule. But our next derivative becomes more complex. Why? It's a product rule. It's a product rule. And why is it a product rule? Well, this first one was not a product rule because this is a constant multiplier. This is differentiable multiplier. So I have to use a product rule. No, because the order of operations says I would have to do this first before I distribute. Right? Now, could I put this on the bottom and use a quotient rule? Could. It doesn't necessarily make it any better though, does it? So I'm going to do it, and I'll write this one out because it's a little bit more complex. I'll call my U this. I'll call my V this. The derivative of U is simple. The derivative of V is the derivative of this, right? So again, chain rule, right? 2x times -2 of this to the -3. All right, so I got all my tools to write my second derivative. So my second derivative is uv prime plus u prime v. Right, and Kara, this is the point where, you know, we probably get a little nervous. We're like, oh my God, I got all these negative signs, but you know, I think we can make it look a little bit nicer because I got some negative powers, and this is the tool that I need to do the job. So I might as well make it look good, right? So I got negative 12x times 2x times negative 2. That's 48x squared. And this is to a negative power, so can I put that in the denominator of a fraction? That seem okay? So I'm going to rewrite this as, so I got 48x squared over that. That's that first thing, right? And then I got plus negative 12 over x squared plus 3 squared. All right. Beautiful. Look at that. What a nice problem. Don't we like to put these two fractions together in order to do this? What's the problem here? The denominators are not the same, right? Well, if this is, yeah, if this is cubed, if I just multiply this by another x squared plus 3, I'll have it, right? So I'm going to multiply the top and the bottom by an x squared plus 3, and then it'll match that, and I can put them together. So if I do that, it looks like this. Which I distribute that negative 12 and combine my like terms, and I wind up with this. Boom. And there is my second derivative. So why did I just go through all of that hassle? Well, I went through all of that hassle because this is the tool to do the job, right, Michael? So what do I want to know about this tool? I want to know where it equals 0, and I want to know where it doesn't exist. Now, before I do that, is there any restriction on the domain of my original function? Now, to look at my original function, I'm just going to rewrite it. Oops. Isn't that my original function? Right? The only thing I would have to worry about in terms of a domain restriction for a fraction is when the bottom equals 0. Well, what am I doing to the bottom? I'm squaring the x, and I'm adding 3. What does that guarantee the bottom never is? It's never 0. So is there any restriction of domain? No. So in terms of critical values, I don't have to worry about that. I also don't have to worry about rejecting anything, do I? Make sense? All right, so things you want to keep in mind. So can this ever equal 0? Well, it would equal 0 if the numerator did, right? And that would give me a PIV. So my potential inflection value is where this equals 0. All I did is add 36 and take the square root, right? Now, guys, if x squared plus 3 is guaranteed to be positive, then x squared plus 3 cubed is also guaranteed to be positive, right? So is there ever going to be a value where this derivative doesn't exist? No. So the only thing that matters now are these two inflection values, possible inflection values. What do I need to do? Well, I got to make sure that there were changes in concavity, right? Because if they weren't, there's no inflection points. So let's check out our concavity. And I'm using this to plug into, right? So negative 10. Negative 10 squared times 36 minus 36, what's that going to give me? Positive or a negative value? Positive value. Why? Because what's the bottom guaranteed to be? Positive. So positive over a positive guarantees me a positive. Plug in 0. 36 times 0 squared minus 36. Negative. Plug in 10. 36 times 10 squared minus 36. Back to being positive. So what did we do? We went from a positive to a negative. We went from a negative to a positive. We've already said that these are in the domain, right? So I am concave down from there to there, concave up on that interval, and I have an inflection point at x equals positive and negative 1 because that's where the concavity changed. Now that problem took us like 13 minutes, right? So I'm going to tell you that we're going to do this next problem. And you're probably thinking to yourself, well, no, you're not, dummy. You only got like 8 minutes left here, right? Not even. Yeah, we do. What time are we done? 9 after? 6 after. 9 after. 9 after. Well, we got 11 minutes. And if you're explaining this, and clearly there's more to it. So you're thinking, okay, to do this, I'm going to take two derivatives, going to do a sign analysis, right? Okay. Well, here's the thing. Michael's looking at this thing differently. You know why? Because Michael's a little more, maybe a little smarter than your average bear. He's like, I'm not doing any of this calculus garbage. You know why? I really actually paid attention in pre-calc. And I remember a whole unit where my teacher had things like this on the board and listed out a whole bunch of things about rational functions. How do you get a y-intercept? Plug in 0. If I plug in 0, what happens to this x squared, this x squared? What's left? Negative 1/4. Do you guys agree that vertical asymptotes occur when the denominator of something equals 0? So would you agree that were I to factor this, I'd have vertical asymptotes at positive and negative 2? Would you agree that there are no roots? And why are there no roots? Because the numerator can't what? Can't ever equal 0, can it? There's no way x squared plus 1 will be 0. So there are none. What's the degree of the top? 2. What's the degree of the bottom? 2. And when the degrees are the same, you're supposed to divide the coefficients. And so you took all those facts in pre-calc, right? And what'd you do? Well, you plotted them. And you hoped that you could play connect the dots. Right? Like, God, I hope I could play connect the dots.
The level of like meticulousness with which you had to like analyze these functions was also like a question like that could take up a ton of time. But like it seems so like simple. Wait, you have the test.
Right there.
There it is. This one. Yeah. All right. But by the way, hey, increasing concave down inflection points, right? So like this isn't like new, okay? I know I'm sort of like explaining it as being new, but it's not. Yes, I used to teach pre-calc. So here's what we got, right? We have a y-intercept at -1/4. That's right here. That's the only point we got. So now you got to be smart about this, guys. Guys, there are no roots between these asymptotes, right? If there are no roots, there's no way I can cross this, right? So it's got to be this, right? Again, how do I know that? Because I know I got to go through this point, and I know there are no roots. So there's no way that it can go up here, right? And if this is going down, then this one's going up. And the same can be said here. And so that's what your graph looks like. Now, what took longer? For me to do that, or for you to take two derivatives using the quotient rule? Not to mention the fact that it's really nice to know what this looks like ahead of time. It's not always going to work, but there will be cases where you may be able to do something like this. You may have, that is possible. But again, even if I give you a weird, actually, I'm going to come back to this in a minute. Yeah. Yeah, if this one equals this one, you take the coefficients. If the top degree is less than the bottom, it's 0. If the top degree is more than the bottom, then you have to synthetically divide or use long division to find a slant. Now, by the way, looking at this curve, what did you have to answer? Where is it concave up? Where is it concave down? Where's this concave up? -infinity to -2, and from 2 to infinity. Where is this concave down? -2 to 2. So is there a change of inflection at -2 and +2? Yes, there is. However, it can exist because -2 and +2 are not within the domain of the original function. Instead, what's there? The asymptotes, right? So here we see a visual example, guys, of where concavity can change, but inflection points don't exist. I told you guys